I'm Tsuchiya. Today, I'd like to talk about my study titled Identification of the Influence of Phonon Scattering on the Electron Mobility in a Strained Silicon Quantum Well. Collaborators are shown here. Professor Sawano and Professor Shiraki in Tokyo State University provided the sample we used in this study. First of all, let me introduce the background. Instead of miniaturization, the strained silicon is an attractive solution to realize low-power MOSFET. The MOSFET with silicon germanium heterostructures was proposed as shown here. The electron mobility at room temperature in silicon germanium heterostructures is about 2 times higher than the mobility in bulk silicon. This is the schematic diagram of silicon germanium heterostructures. There are advantages and disadvantages in this structure. The advantage is removal of ionized impurity and silicon oxide interface. The electrons are supplied from doping layer to strained silicon layer by modulation doping. The separation of electron from ionized impurity suppresses the ionized impurity scattering. By modulation technique, we can generate two-dimensional electron gas or 2-DEG without silicon oxide interface like MOSFET. This interface causes the scattering due to the charge trapped at the interface. So we avoid the scattering of interface potential using silicon germanium heterostructures. As a result, we can focus on only phonon scattering. Phonon scattering is one of the essential scattering factor for MOSFET. So we need to investigate the phonon scattering closely. However, there is a disadvantage of this structure. The advantage is difficulty to measure 2-DEG mobility because of parallel conduction. Parallel conduction is in silicon germanium virtual substrate or a doping layer. For example, when we measure the mobility by Hall effect measurement, the average mobility is obtained. The mobility in parallel conduction is lower than 2-DEG mobility because of ionized impurity and defects. So the average mobility is also lower than the 2-DEG mobility. So to investigate the phonon scattering closely, we need to extract 2-DEG mobility apart from parallel conduction. There are many reports about calculation of the mobility, but few reports about the experiment. This figure shows the absence of experiment. This figure shows the temperature dependence of the mobility. The solid line shows the calculated mobility in strained silicon. The dashed line shows the calculated mobility in bulk silicon. The crosses and circles shows the experimental value of the mobility in bulk silicon. So there is no experimental value of strained silicon. So on the other hand, our group set up the mobility spectrum analysis or MSA MSA achieves the extract of 2-deg mobility. So by using MSA and silicon germanium heterostructures, we can investigate the phonon scattering closely. So the purpose of my research is to identify the influence of phonon scattering on the electron mobility in a strained silicon quantum well. This is the structure of my sample. This sample was grown by MBE in Siraki group. The germanium content is 30% and the depth of strained silicon layer is 15 nanometer. The amount of doped antimony is 3 times 10 to the 12 per square centimeter. This is a measurement system. This system enables us to measure the magnetic field dependence of resistivity. With this superconducting magnet, the magnetic field is applied. In a magnetic field, we pass the electric current and measure the electric current and two voltages, Vxx and Vxy. By this measurement, we can obtain the two resistivity, rho xx and rho xy. These resistivities are converted into conductivity, sigma xx and sigma xy. We repeated the same procedure, changing the amplitude of magnetic field. As a result, the magnetic field dependence of conductivity is obtained, as shown here. MSA is performed with this result. This figure is same as the slide. This figure same as the figure in previous slide. MSA is based on these expressions, so I will explain these expressions simply. So let us consider the two conduction case in a magnetic field. The conductivity in a magnetic field is represented the sum of conductivity in each conduction channel. Each conductivity is represented like this. So replacing the conductivity at zero magnetic field into with the partial conductivity S mu, we can reproduce the above expressions. So partial conductivity means the conductivity at zero magnetic field in each conduction channel, labeled by the mobility. Partial conductivity is distinguished from another partial conductivity. Substituting this result into these expressions, partial conductivity is obtained as shown here. The peak position of partial conductivity shows the mobility in each conduction channel. The sum of partial conductivity in each peak corresponds to the conductivity in each conduction channel. Using these simple expressions, the carrier density in each conduction channel is obtained. As a consequence, the following are obtained by MSA: the number of conductions, each mobility, and each carrier density. This figure shows temperature dependence of electron density. 2-deg represented by blue and parallel conduction represented by red is obtained by MSA. The 2-deg density times 10 to the 11 per square centimeter is independent of temperatures. Parallel conduction through antimony doped layer exists from 7 to 300 Kelvin. In order to reveal the reliability of MSA, we calculated the average density. Good agreement between hole density, represented by green, and the average density, represented by black, demonstrates the reliability of MSA. This expression was used when the average density is calculated. This figure shows the temperature dependence of the electron mobility. Two-degree mobility deviates from the whole mobility above 100 Kelvin, so this result indicates the need of MSA. Good agreement between whole mobility, represented by green, and average mobility, represented by black, demonstrates the reliability of MSA. I listed the mobility at room temperature. The mobility in this work is higher than the mobility obtained by Hall effect measurement in silicon-germanium metal structures. And this mobility is close to the record mobility obtained by MSA. So the scattering, except for phonons, is fully suppressed, and this sample is appropriate to the investigation of phonon scattering. Before the explanation of calculation, let me summarize the electron distribution in strange silicon quantum well. In bulk silicon, there are 6 hole degenerate ballates. In silicon quantum well, by the confinement effect, the 2 ballates in the direction of confinement exist in the center of K space because of inability of periodic condition. When stress is applied to a silicon quantum well, the energy of 6-fold degenerate ballate split to the energy to 4-fold degenerate ballates and 2-fold degenerate ballates. The energy splitting is proportional to the germanium content. The content of our sample is 30%, so the energy splitting is about 200 millielectron volt. This energy is much higher than the thermal energy at room temperature, so electrons exist only 2-fold degenerate ballates. In the following calculations, I assumed that the electron distribute in only 2-fold degenerate ballates. Scattering is based on Fermi's golden rule, so we need to obtain the wave function. By confinement effect, we cannot apply the Bloch function to the wave function in the direction of confinement, so we need to calculate the wave function. The method to calculate the wave function is self-consistent solution. This solution is based on the iteration with Schrödinger equation and Poisson equation. First, we set the initial potential and solve the Schrödinger equation. Using obtained wave function, Poisson equation is solved. Using obtained potential, the Schrödinger equation is solved again. By this iteration, we can find an actual wave function. These are conditions for calculations. The energy difference of conduction band between silicon and silicon germanium is 200 millielectron volt, and the energy difference between 2-fold and 4-fold generator Barry is 200 millielectron volt. The effective mass of strained silicon is equal to the effective mass in bulk silicon. The dielectric constant of silicon germanium is slightly different from the dielectric constant of silicon. Now we assumed that the dielectric constant of silicon germanium is equal to that of silicon. The background acceptor is 1.0 times 10 to the 15 per square centimeter. This is the example of self-consistent solution. Upper figure shows the wave function. In this figure, the wave function of ground level and ninth energy level is shown, and the lower figure shows the energy levels and potential. The energy of ninth energy level is about 150 millielectron volt. This energy is much higher than thermal energy at room temperature, so electrons hardly exist in this energy level. Actually, the calculated electron density of this energy level is below 1% of the calculated electron density of ground level. So we omit the higher energy level in this calculation. There are two types of scattering. One is intrabarrel scattering. The other is interbarrel scattering. There are two-fold degenerate barrel in the conduction band of a strained silicon quantum well. So intrabarrel scattering is a scattering in a barrel, and the interbarrel scattering is a scattering from a barrel to the other barrel. This figure shows the Phonon dispersion relation. The intrabarrel scattering does not change the momentum of electron because the electrons intrabarrel scattering occur around the edge of barrels, so only the phonon around 0 point contribute to the intrabarrel scattering. The Hamiltonian of electron acoustic phonon interaction is described here. Acoustic phonon displace the neighboring atoms in the same direction, so the first order change causes the disorder of potential. D is deformation potential. These are assumptions for calculation: elastic scattering, parabolic band, and deformation potential. Now, let us comment about deformation potential. This is a list of deformation potential and energy. There are many reports with different deformation potential. Now, we are discussing intrabarrel scattering, so please focus on the deformation potential of intrabarrel scattering. Many reports use 0.9 electron volt as deformation potential, but LA and TA phonon contribute to the intrabarrel scattering. Pop used two values for the calculation, so I adopted this deformation potential in my calculation. There are two types of scattering, even in intrabarrel scattering. One is inter-subband scattering, and the other is intra-subband scattering. Electrons are confined in the z direction, so discrete level is generated. These discrete levels form the parabolic band in plane direction, so subband is generated. As the energy of electron increases, the number of subband increases and the scattering rate also increases. This behavior is well shown in this figure. The horizontal axis is energy and vertical axis is scattering rate. As the energy increases to the next energy level, the scattering increases like a step function. The calculated mobility at 300 Kelvin is 2,580 square centimeter per volt second. So next I will explain the intervalley scattering. Although we cannot apply the periodic condition to calculate wave function, here we assumed that the tendency of periodicity and band structure remains. So phonons contributing to the intervalley scattering is same as the phonons in bulk silicon case. So the Hamiltonian of electron acoustic phonon interaction and electron optical phonon interaction are described like this. Unlike acoustic phonon, optical phonon displaces the neighboring atom to the opposite direction. So the zeroth order change in lattice spacing causes the potential disorder. The deformation potential is set to these values. This is the list of deformation potential. So please focus on the deformation potential of acoustic phonons. Many reports treated zeroth order acoustic zeroth order change. However, the acoustic phonon scattering is induced by first order. So the Dolph's treated deformation potential as first order. So I adopted this value for the calculation. As a result, the calculated mobility at 300 Kelvin is 2.23 10 to the 4 square centimeter per volt second. This is the detail of calculation. If you have a curiosity, please check it. This figure shows temperature dependence of 2D mobility. Straight line shows the calculated mobility. The red line corresponds to the mobility involving only intervalley scattering. The green line corresponds to the mobility involving only intervalley scattering, and blue line corresponds to the mobility involving both of intravalley and intervalley scattering. As you see, intravalley scattering is dominant in this temperature range. I listed 2-degree mobility at 300 Kelvin. The calculated mobility is lower than the mobility obtained by MSA. I have not determined the cause, but a likely explanation is that deformation potential is not appropriate, or phonon dispersion relation change in silicon-germanium heterostructures. This is the conclusion. Temperature dependence of 2-degree mobility were obtained by MSA. Wave function in the confinement direction is calculated by self-consistent solution. The calculation of scattering rate is performed based on appropriate physical implementation about deformation potential. The calculated mobility is lower than the mobility obtained by MSA. So we need to determine the cause of this difference. That's all. Thank you for your kind attention.